I'm Prabha, Assistant Professor of Chemistry, A.D.M. College for Women, Autonomous, Nagapattinam. Today's class we will deal about NMR spectroscopy, which is mainly concerned with nuclear magnetic resonance and the spin interactions. As we understand nuclear magnetic resonance spectroscopy, every nucleus is associated with a spin. As a consequence of spin, there arises magnetic moments. The angular momentum, which is a vectorial sum of the orbital angular momentum as well as intrinsic spin angular momentum. So the vectorial summation of these two parameters put together is nothing but the nuclear angular momentum, and it is arising because of the nuclear spin associated with each of the nucleus. And every nucleon in turn will add up together, that it's a vectorial sum of all the nucleons. And then again, we can also understand that the intrinsic spin angular momentum is a coupling of L and S parameters, which is the coupling factor which is responsible for this value of intrinsic spin angular momentum. So the resonating parameters or the magnetic field that resonates is a summation of all these and the vectorial summation of all the nucleons that are present inside the nucleus. Then, as we say, the value arrives as the nuclear angular momentum will be equal to h into I, where h being the Planck constant and I refers to the nuclear spin, or also referred as the nuclear spin angular momentum, which comprises of all these parameters. Now, if you understand that, this can take up the values, which means that nuclear angular momentum h into I can take up either half integral values or whole integral values. So that is dependent upon the mass number of the nuclei, whether it is an odd mass number nuclei or an even mass number nuclei. Then again, intrinsic spin angular momentum is given by the expression 1 by 2 of h into I, where I represents the nuclear spin, and here this then again can take up integral values as half values or as whole values. This in turn is again dependent upon the mass number of the nuclei and each of the nucleons that is present. So that will give rise to a set of parameters or the probability factors which can take up odd or even number of nuclei. As we understand, odd number of nuclei, say for example we take it up, odd number of nuclei will arise when there is one set of odd protons, another set being an even number of neutrons present in the nucleus. This is one case. Another one is set B, which is odd number of protons, and the other set which we can take it up as odd and even nuclei. Even nuclei can take up both the values of protons and neutrons, either even, or protons and neutrons can be as odd. And the other one set of parameter that will arise here, proton plus neutron, which are the nucleons that are present, has to be one even and the other one as odd. And proton plus neutron, the other set which is odd number of protons and even number of neutrons. So these are the four parameters that occurs, or the possible ways of getting nuclear interactions that happens, and it is mainly dependent on the mass number, and this will give rise to atomic splitting of spectral lines or the hyperfine splittings, which we call it, and that is mainly observed in cases where there exist isotopes. So this has been in study that we understand nuclear spin and its interaction, and thereby the signals can be computed to observe an NMR spectrum. So the basic understanding involves all these understanding, and here the nuclear magnetron value, which is nothing but the mu value or the field magnetic moments that are associated with each of the nucleons, is given by the value of E of h divided by 4 pi m into c. And the values that have been computed as 5.02 into 10 power minus 27 Hertz. And there arises another parameter that not only the nucleons can interact in a field or that is associated with a field, but there lies an interaction between the nucleons and the external electrons that are present. So the charge density or the charges that it can interact with that is another factor which we call it as a quadrupole resonating system or a quadrupole resonance. Here, as we understand, this is a resonance that happens, or the interaction between the nuclear spin of all the nucleons within itself is nothing but NMR spectroscopy. The interaction of nucleons that are present in the nucleus within itself, in addition to that, it is also interacting with the electronic spin, the magnetic field oriented with that. That interaction gives rise to the electronic quadrupole moments, which is expressed by the factor Q. And that is given by 2 by 5 into E into A minus B. So now we understand that there exists the set of resonances or the nuclear spins can be classified as I is equal to 0, a system where there lies no nuclear spin interactions, which means that it cannot produce an NMR spectrum, or there lies no nuclear magnetic moments associated with it. There arises another parameter which is I is equal to 1 by 2 and the other one which is I is equal to minus 1 by 2. If I is equal to 1 by 2, which is the nuclear spin has a half integral value or a whole integral value, but value arrives there as 1 by 2, then that is associated only with the magnetic moments, which means it can give out an NMR spectrum, or it has a flux that can interact with the varying field that if it is applied externally, or there is a magnetic moment that is associated with all the nucleons that are present inside the nucleus. The other case with I is greater than 1 by 2, which is in addition to the nuclear magnetic resonance spectroscopy, there is also quadrupole resonance which arises because of the interaction of the magnetic field that is generated by the nucleons present inside the nucleus and the electrons that are present outside the nucleus, which we call it as the interactions as nuclear quadrupole resonance. As we understand, the distribution of nuclear charges that gives rise to quadrupole nuclei, that which is referred as the deviation from a spherical system to an ellipsoidal system. When there is a uniform distribution or a symmetrical distribution of charge density between the nucleus and the electrons, then that is referred as a spherical system, which gives rise to only the NMR spectrum. The other one case where the spherical system is distorted into an ellipsoid. So that is the case which we call it as an unsymmetrical distribution of charge density or the magnetic interactions between the nucleons and the electrons that are present outside the nucleus are being as ellipsoidal, where there arises two cases that the ellipsoids can be as a positive or prolate oblate type, or otherwise as an oblate type, prolate type or an oblate type. That it can give rise to positive Q values and the negative Q values. The second parameter, which is nothing but the unsymmetrical distribution of magnetic flux density or the charge density between the nucleus and the electrons, is responsible for NQR spectroscopy, which we call it as nuclear quadrupole resonance, in addition to the NMR spectroscopy. The first parameter will give rise only to nuclear magnetic resonance spectroscopy. And the expression that we have arrived at in previous step, that the value of Q being given by 2 by 5 of the charges into A minus B, where A and B refers to the semi-major and the semi-minor axis of the ellipsoid, and the charges being multiplied by that parameter into 2 by 5 gives the quadrupole resonating factor given by Q. Next one is, what do we analyze in an NMR spectroscopy? Just an outline of this. Here, as we understand, we can record a NMR spectrum by continuous wave method or an FT-NMR method. In continuous wave method, we apply an electrical field gradient of the order of radio frequency range around 100 MHz in the system, that we place the sample perpendicular to the applied magnetic field. Then the developed field, that is the resonating field with the applied magnetic field, will have the tendency to oppose the external magnetic field. So those are the parameters that we will discuss in next hour, that what are the effects that are produced in any sample or that contains a proton, and that is different because of the different environment that exists in the protons. Then what are the consequences and different effects, which we call it as chemical effect, and the parameters due to electronegative factors and spin-spin splitting. Next other one is here, as we understand. So as the electromagnetic radiation being absorbed by the sample, there arises a decrease in intensity of the emitting radiation as it passes through, and the emitted radiation frequency is absorbed by the recorder and then it is analyzed. So there will be a decrease in intensity, which can be expressed as a domain factor of time or a domain factor of frequency. So we get two types of curves. One is a unresolved one, which is a continuous, there is the outcome of the continuous wave method, one graph which corresponds to the graph that expresses the field gradient as a decreasing parameter of this is referred as a time domain graph. As time proceeds on, what happens to the decrease in the intensity of the system? The other one as a frequency domain to resolve the components, how the frequency being resolved, that is given by, and this is given by 1 by P, and this is a factor of pi divided by T prime. Sorry, this one is pi divided by, there is one wave amplitude pi component, and that is being resolved into the parameters to observe that, which we call it as a frequency domain system. And these are the outcomes of the continuous wave method. And the continuous wave method is that where we apply an external magnetic field and observe what happens with the resonating magnetic flux that is developed in the sample of the molecule that is placed under observation. The next one is an FT-NMR. FT-NMR method is a Fourier transform method where we implicate the signals are being computed and then it is analyzed by the system, or in the method of computational analysis. So here also this is more preferred for the reason that it is so much accurate and precise, and also this is applicable for the systems where there is lesser percentage of abundance of the existing molecules. Say for example carbon 13, where the percentage abundance ratio is lower, then this system of FT-NMR computational analysis can give an absolute idea about the protonic, that is the environment or the isotopic environment that is responsible for the magnetic flux that in turn can resonate with the external applied field. And here the magnetic field gradient, that is as an outcome, which has a decreased intensity value, is computed graphically as a frequency domain. So that is here as the frequency gradient, it is transformed, and that is the computational analysis that is being involved in Fourier transform method of analyzing any given sample. As we understand the parameters of NMR spectroscopy, the effect that is caused, one of the effect that is caused is chemical shift. This chemical shift obviously refers to the interaction or the splitting of the observed NMR signals, or the impact of the electronegativity and the charge density that already exists in the system. So to understand this parameter, we will take two molecules in the examples. One is acetylene molecule, another one is ethylene molecule. So now to understand the impact of electronegativity, acetylene has more electronegativity because of the triple bond that is present in it, and ethylene comparatively has lesser electronegativity because of the double bond. As we understand this, then there is another factor that is also playing a major role, or that is a consequence of this nuclear magnetic resonance, is nothing but diamagnetic anisotropy. So as we understand, first we should understand what is the role of electronegativity on any system. Higher the electronegativity that exists in the molecule, then the more will be the de-shielding effect, and as an outcome of the de-shielding effect, there will be a downfield shift in the observed delta values, or the observed shift values, or the chemical shift values of that. So this is the impact of electronegativity. So to understand the order of electronegativity, we take the proton environment as the same, but the impact of the electronegativity that is implied on the system as it differs, we understand. Methyl fluoride will be more de-shielded, methyl fluoride, because of its higher electronegativity values, that will have more de-shielding effect, and in that case, more de-shielded values, or the delta values will have a downfield shift. and methyl iodide as comparatively lesser in its electronegativity parameters will be shielded. In other words, we say that lesser be shielding. In other words, we say that it will be more efficiently shielded and will have an upfield shift. So this system of shielding will have an upfield shift of delta values. So if this is the parameter that is happening in the system, then that which has to be observed as here will be more electronegativity in acetylenic molecule, so it has to be more deshielded. But this is not there. This is not the observed one as per the nuclear magnetic resonance that takes place in these molecules when they are subjected to sample irradiation. So that is another role that plays a major part in determining the shift values is nothing but the diamagnetic anisotropy. Here, ethylene molecule being the linear molecule has a linear symmetry, then the association of the magnetic field around the pi molecular axial orbitals, pi orbitals that are present along the molecular axis has some significance that is referred as a diamagnetic anisotropy, whereas comparatively in ethylenic system, this is a planar molecule where the bond effects or the negative effects that is lying above and below the plane, and there is a reason for the controversial observations, because as per the electronegativity values, or if we take into account their plays in some part of electronegativity parameters in the observed NMR spectrum, then it has to be the other one. But of actual observed values account for the parameter which we call it as diamagnetic anisotropy, which is mostly dependent upon the symmetry of the molecular system that interacts with the nuclear magnetic field that already prevails in the molecule and the external applied field which is applied in a way which is perpendicular to the system, and the sample has a field or the lining up of the magneton values to oppose the external magnetic field. So these are the components or what is the impact of chemical shift, or the features of chemical shift which arises because of the consequence of nuclear magnetic resonance. As we understand the other parameter which is a consequence of nuclear magnetic resonance, nothing but spin-spin splitting. So the splitting of the neighboring environmental protons that interacts with the already existing magnetic resonance, that is causing the signal lines to be split as a hyperfine splitting, and the effect is referred as spin-spin splitting, and it is an inverse case of spin-spin coupling. But to measure the parameter or the magnitude of spin-spin splitting will be measured in terms of spin-spin coupling values, which are referred as the J values. So as we understand here, there lies an interaction between the nuclear magnetic resonance or the resonating field or the resonating flux, a variation in intensity of the magnetic field that is arising with the sample and the external magnetic field that is imposed on the system, and also there lies a resonance with the protonic environment that is neighboring to that of the already existing environment, which here, as we take it up example, will be still not here as we consider the number of signals that are observed in an NMR spectrum of ethane molecule and propane molecule. Here, these are considered to be as chemically equivalent environment, and thereby there are observed two methyl protons are considered to be existing in the same environment. As we use a low resolution spectrometer, the hyperfine splitting or number of splitting signals won't be there, and if we use a higher resolving parameter, that will resolve each of the components into the intensity ratios. So as we understand, there lies only one NMR signal, whereas as we consider ethane, there will be two signals because two methyl environments are considered to be a same protonic environment, and one is that is because of the ethylenic environment. Two methyl environments of same, or they are supposed to be existing in the same environment, or they have the same protonic environment or the varying magnetic flux density. The next is as we use a higher resolving parameter. So what is the splitting that can be observed because of the resolving parameters? We have to understand that this protonic environment where there lies the same environment as in the case of ethane has no significance, whereas as the chain length increases or as the number of the environment of protons increases. Then, in that case, there is hyperfine splitting observed, and here, as we understand, two methyl environments, and this is supposed to contain two sets of methyl environment. One is a methyl environment, another one is a methylene proton. So, methyl proton, another one is a methylene proton. The methyl proton will be split up as 2 plus 1. So, the neighboring environment that is imposing this methyl proton, and we have to see, and this is the same as that. So, we consider these two methyl environment or the methylene protons as to be one and the same. So, here 2 plus 1 that imposes as 3 signals which are observed, and they are observed in the intensity ratio 1:2:1. The other one is the methylene proton. Here it is 3 plus 3. Then the next one splitting up as n plus 1 parameter. So, there arises 7 number of spectral lines, which means we understand here these two signals are split up into a fine splitting as 7 number of spectral lines in the intensity ratio as 1:15:15:1. And this is in accordance with the Pascal's triangle that defines the intensity of the hyperfine splittings that are observed because of spin-spin splitting effect. So, as we understand, number of signals that are observed or the number of hyperfine splittings that are observed because of the neighboring protons is referred by the factor n plus 1. And this n refers to the number of neighboring protons, and the coefficient of 1 plus x the whole power n is defining the intensity of the spectral lines that are observed in the NMR spectrum, and the intensity is governed by regulations of the Pascal triangle, how to arrive at various intensity ratios as we proceed on from the number of proton environment as the chain proceeds on. So, we will also take the n-butane and n-pentane system to arrive at what are the intensity ratios that are existing in the proton environment, and then also we will arrive at how many number of signals are formed and how the hyperfine splittings can be justified based on the spin-spin splitting effect, and the magnitude of the spin-spin splitting effect is governed by J values, which we call it as the J values, nothing but the spin-spin coupling constant J. Now we have to justify the intensity ratios that are observed in the spectral lines. Here, say, if you take it as the example N-propane, there arises different environments of methyl protons and methylene protons. Even though two methyl protons are there, are considered to be chemically equivalent methyl protons, and one is methylene proton. Here, the methyl protons, which are equivalent, can interact with the methylene protons labeled as A and B. The protons which are present in the methylene part labeled as A and B in 4 different ways. One is both the methyl protons can interact symmetrically with the methylene protons or unsymmetrically with the methylene protons. The other one is the third case, and the fourth one, two of the methyl protons can interact as one with symmetrical system, the other one with an anti-symmetrical system, and vice versa. Now we have to account for the ratio as 1:3:1. Why not as 4 intensity signals? That is because the last two are equivalent in their energy, and hence the splitting of the spectral lines will be in the intensity ratio as 1:3:1. So the ratio that the third case and the fourth case being identical in their energy makes the justification of the splitter parameters of the intensity of the observed NMR signals in the ratio 1:3:1 for N-propane system. So we understand the spin-spin parameters such that the impact that is produced in the NMR signal can be understood.